Okay, our session is being recorded as always. Welcome to week 8. I'm very happy to say for the first time in 5 days, I have internet connectivity, so it's been a bit of a struggle, which is why your slides for this week, the view graphs you see on the screen and we'll see, were not uploaded until just a few minutes ago. The Time Warner people came through at the last minute and got me a reasonable internet connectivity. I was able to sponge off my neighbor, who's also my son-in-law and daughter, and use theirs, but I certainly need to have connectivity that I can rely on a little bit more and a little bit faster than what they had. So anyway, no excuses for me not to be on the ball here. So I'll get caught up on things, but again, these view graphs are out there now, and I think you'll find this an interesting aspect of the course. Now, again, quick background, I've taught entire courses in artificial intelligence, and of course neural networks is part of the AI world as well as being part of the analytics world. And so it's one of my favorite things, along with genetic algorithms. Neural networks, genetic algorithms are two of my favorite tools because they appear, and some would say they do, learn on their own. Now, it depends on how you want to define learning. When you start with a neural network, it has no clue what the answer is, and it goes through an iterative process and learns the black box in the middle that causes the inputs to be related to the output. Now, you could say, well, doesn't a regression model do that? A regression model, a little something different. It's doing a statistical building a model, whereas a neural network, and to a lesser extent, well, not a lesser extent, but in a different way, a genetic algorithm is actually learning. So once you get a neural network going, you can give it the go signal and go do something else while it learns on its own. You don't have to hold its hand or do anything once you get it set up, as always. Now, with powerful packages like SAS Enterprise Miner, the neural network training for a reasonable sized neural network appears to happen instantaneously. It actually is not. The first neural network I built back in the 90s with a $20,000 add-in board that we bought to add into my, I believe it was a 286 computer from Xerox or somewhere. $20,000 board just so we could build a small neural network and show the students at the National Defense University where I worked something about neural networks and how they mysteriously were able to learn relationships. Now I'm very much impressed by the fact that we can take pretty large size problems and hit go, and the neural network will be finished, if you will, within a few seconds. Now, of course, with a large problem, that's not going to happen. But neural networks do, once they learn, then of course they can be saved and they execute almost instantaneously, which is why almost all large credit card issuers, for example, use neural networks to detect fraud. They work extremely quickly and they're very accurate and so forth. Now, again, as a little bit of a background, you will notice in this course, and this is kind of a traditional approach, we went from a very simple, straightforward predictive modeling tool, decision trees. I don't want to denigrate them. They're very good. Easy to explain, easy to build, easy to use, and oftentimes very accurate. To a somewhat more complex tool, or substantially more complex tool, regression, where we have a logistic regression and linear regression, and we have a lot of things we can tweak and bells and whistles we can set, and settings, and try to get a statistical fitting to something that's a little more complex than what a decision tree will easily fit. And now we're moving into the final stage. Neural networks are designed for extremely complex relationships, nonlinear relationships. They do quite well at figuring out what's going on. However, the downside with neural nets, as we'll say a little bit more about tonight, is, of course, they're very difficult to explain and somewhat difficult to even understand. I think they're, almost magical if you can peer behind the scenes and actually see what's going on. It's understandable, but it appears to be a very interesting process. So let me start and say a few things about them. And then next week, as always, we'll take a look at how SAS Enterprise Miner handles neural networks. And I think you'll find that interesting. I think the SARMA chapters on neural networks are excellent. So chapter 5, I believe it is. You'll find a lot of good reading in that. So let's save that for next week, but let's go ahead. As always, I like to have a little agenda. As you know, I wander from the agenda frequently, but at least I have one. A little bit of a background, and then we'll go through sort of step by step what's going on behind the scenes, which has been my approach for all of these techniques. You'd like to know exactly what's going on, because if you have to sell an analytical output answer to a problem that you've built with the neural network, you're going to have to do that. You're going to have to articulate what went on and why in layman's terms as best you can, because it is a little bit mysterious. So we'll go through that. We have about 100 billion neurons in our body. Well, we don't really understand everything about them, but our biological neurons are essentially on-off switches. Okay? Now, what makes them interesting is that there's a lot of inputs. Okay? We call the inputs dendrites. They're carrying in signals. Something mysterious, not quite well understood yet, goes on in the nucleus, and depending on whether that reaches an excitatory or a dampening signal, it sends out a signal. Each neuron can send out a signal, just one axon, but that axon can be connected to hundreds, if not thousands, of other dendrites, which are inputs to other neurons. So it's kind of a layering effect. I'll try to explain this a little bit in terms of a learning thing, but basically the learning takes place as the signals strengthen between neuron to neuron. We call that learning. And that's really it. Again, mysterious, isn't it? How we can do so many things with just 100 billion of these neurons. But they are massively parallel connected. So think about a computer, which is basically on-off switches also, and we do quite wondrous things with that. So about 100 billion neurons, many with up to 1,000 connections. So what happens here? Well, information flows in via the dendrites. Something happens, as I said, in that nucleus, and then a decision or an input or a boost or a signal flows out via the axon to other neurons. Think about, the best analogy I've ever been able to come up with is if you've raised a child, you will sort of see this happening as the neurons begin to form and they begin to strengthen and they begin to connect, and the child begins to understand language and be able to read and do math and learn. Now, to take it to a simple level, suppose you take a young child and show them a pine tree for the first time. And you let them touch the pine tree, you let them smell the pine tree, you let them see the unique shape of the pine tree, feel the pine tree, rub the bark, etc., and you say pine tree. Well, they've been getting inputs through the various senses, their nose, their eyes, their hands, as they touch and see and smell. They could even taste it, I guess, the pine tree. And so these are all sensory inputs, and they get connected to an axon, to a neuron that represents pine tree somehow. So that when you say, guess what that is a pine tree, they sort of get the connection. Now, if you did that one time to a child, and then took them away for 50 years and never saw or heard or read about a pine tree again, likely that learning would fade, go away, dampen certainly. What if they hear about it every Christmas time or see it in pictures or see it on TV? It comes back to mind. So we all pretty much have an image of what a pine tree looks like. And we know about the needles being sharp, and we know about the nice smell, the aroma, and the texture and everything. So that's learning, isn't it? Well, that's basically what happens as best we understand it. And so what that means is we are pretty good at recognizing sort of what we call patterns. Okay? So many of the functions our brain accomplishes are because of this. So pattern recognition is really the key. Now, as humans, we do a pretty good job with certain kinds of patterns. You can see a partial face of an old friend and know who that is. You can see sort of semi-scribbled letters and sort of figure out what the message was meant to be. You can fill in the blanks. If I say tick, you probably think tock. If I say the mouse ran up the clock, So we can fill in patterns of a lot of things. However, and we do this with very fast processing in our brain only because it's parallel. It's actually very slow. It's 1,000 or more times slower than a computer processes information, but because we're doing it in parallel, it appears to be much quicker. We can also learn and adapt. If I say the mouse ran up the, and you say clock, and I say no, the mouse ran up the tree, and that's the new nursery rhyme, you would learn, oh, I see, tree goes there instead of clock. And we degrade gracefully as things begin to be less and less filled out in the pattern. We can still handle it to a certain extent. As I said, you see part of a face of a friend or a family member, you know who that is. And so even a photograph, you can fill in the missing pieces, sort of. So we do a lot of things with pattern recognition. However, we're not very good at recognizing numerical patterns. You know, if I give you a spreadsheet with a bunch of numbers, thousands and thousands of rows of numbers, and said there's a pattern in there somewhere, find it, you probably say, oh my gosh, how am I supposed to find that? Unless it's very obvious, I'm not going to find it. You know, so pattern recognition of a certain kind, imagery, etc., we do well. I mean, if you hit a tank behind a tree, we'd probably say, well, that's a tank hiding behind a tree. I can't see the whole thing, but I can see enough of it to know what's back there. But when you deal with mathematical information, numbers, words, in a big spreadsheet or something like that, and try to find a pattern, it's difficult. So going back to the 1950s, someone had the great idea that maybe we could build a computer that recognizes patterns, or some kind of software in a computer that recognizes patterns, like our neural network does in our head. And they came up with this idea called an artificial neural net. We've sort of dropped the word artificial and call them neural networks now, but they're not really the same as our brain, nowhere near as capable in many respects, but yet very capable at doing certain things that we as humans cannot do. And following what we think is how the brain works. Now, of course, brain knowledge expands every day. We may find out something entirely different about how the central part, the nucleus of the neurons works. But for right now, it's about the best we understand it. Some of you know, if you've been to my website, stevekanoe.com, look, you notice I categorize interesting things I find about the brain. I'm a little behind in keeping that up, but I'll get caught up after this semester. But anyway, the plan was to now see if we could put something in a computer that is similar to how our brain works in the sense that it recognizes patterns. Okay? So it's a small piece of what the brain does. Now, as I said, we learn from having prior data being reinforced. We're given inputs, such as the things I mentioned from the pine tree, and associated outputs with that. Someone says, that is a pine tree, young man. That is a pine tree, young lady. And we figure out the relationship between them. We map the inputs to the answer. And again, that's pattern recognition. So what a neural network in the computer will do is the same thing. It's basically going to take inputs and an answer and build the black box in the middle. Now, that's sort of what a regression model does. It builds a black box in the middle. You have inputs, you have an answer, and you have a black box in the middle. But that black box is a statistical formula that's relatively easy to understand. Certainly with linear regression, each of the coefficients represents straightforward amount that the answer would change if there was a 1 unit change in one of the input variables. With neural networks, that relationship is a little murkier. You'll see why when we talk about how they're built. Yet it's the same concept. Inputs, we say these inputs cause this answer. You figure out how. And the neural network says, well, I'll build this mysterious black box in the middle that will figure out how the inputs are related to that answer. So again, we have to have past data. Now, artificial, and I'll quit saying artificial, but artificial neural networks can do, like our brain, deal with incomplete data. Once you've trained a neural network that needs 6 inputs, if 1 or 2 of those inputs is missing, the neural network will still take a shot at the answer and likely be close as long as the inputs that were missing aren't too substantial. Whereas with a regression model, of course, you'll be able to get an answer. You have to have all the inputs. With a decision tree, you'd have trouble with that. You'll notice that it says fast processing via parallel processing scratched out. And that's because we don't do that yet. We don't do much, if any, parallel processing with computers. They're very fast, but it's still sequential. Artificial neural networks do learn and adapt, if you want to call what you'll see next learning and adaptation. And of course, as I said, they degrade gracefully. So, before we get into the specifics of how they work, here are some very interesting neural network applications. Again, I try to keep up with these things because I'm so fascinated by neural networks. And you can see that there's a lot of analytical ideas on here. You know, predicting bankruptcy, diagnosing turbine engine problems, identifying disease, evaluating cancer biopsies, are they malignant or not, and so forth. Forecasting patient load. Most of these are analytically related to a degree, if not predictive analytics, certainly analytics of another sort. And they're pretty substantial to think that a neural network can outperform humans for many of these. So it's very interesting. Now, we don't try to build an artificial neural network in the computer anywhere close to the size of the brain. Couldn't do that. So we use a simplified architecture. There are many different neural network architectures out there. People have their own. If you're looking for an interesting website, Ward, W-A-R-D, wardsystems.net has its own proprietary software I've used in artificial intelligence courses, and they have their own types of neural network architectures. Okay, but now back to the main point. The main point is about 95+% of all neural network applications use the same architecture, something called the backpropagation. The backpropagation. When you get to reading chapter 5 in the Sarma book, you will see that SAS2 uses the backpropagation as its default. The backpropagation network works quite well. So, I mean, why make something more complex than you need to? It works. And so it's become the go-to network. And if it doesn't work, then you might try one of the more exotic architectures. And I keep saying architectures because you don't really program a neural network. You sort of design it, okay, more than program it. Okay, so the backpropagation network usually has 3 layers to it. It can have more than 3, but 3, again, is the default. There's an input layer, which are, of course, are the key inputs, and we've talked about inputs, predictor variables, just like we did. We had to have predictor variables for decision trees. We had to have predictor variables for regression. We have to have predictor variables, or inputs, I'll call them from now on, for neural networks. Then there's also outputs, which is the answer, the results. And then there's the thing I skipped, the middle layer, which is what we call a hidden layer, and represents a feature collector, but I'll have to explain that in a little more detail in just a minute. So normally we have a 3-layer network called the backpropagation architecture, okay? Now, this is sort of what it looks like. The backpropagation perceptron or multi-layer perceptron network also is fully connected. What do you mean by that? Well, this layer over here are the inputs. It doesn't have to be 3, by the way. This is just a notional representation. It could be just like any other model we built. There might be more. There might be more predictors that are useful. So it has inputs. It has outputs. Now, in a regression model, what do you get for an output? You get one number or one probability. Okay? You don't get multiple answers. But in a neural network, you can have multiple answers. Okay? Actually, you can have multiple answers in various decision trees and so forth too. But we get multiple outputs if we need them. If you're predicting a continuous answer, you're just going to have one here, the answer. If you're predicting a binomial or a bivariate where one represents a 1 and one represents a 0 or a yes and a no, you're going to have 2. And they're each going to end up with a number, and sort of the higher number wins, okay? If it's something with more than 2 outputs, something categorical, which, you know, has 3 answers, high, medium, and low, you may have 3 outputs. And then there's this middle layer. Again, we'll discuss this more in a minute. But the key is it's fully connected. And what do I mean by that? Well, you'll see in a moment, because information is going to flow from the inputs to each of the hidden layer neurons. And it's going to flow from each of the hidden layer neurons to each of the output neurons. These are all neurons, different kinds of neurons, input neurons, hidden layer neurons, output neurons. Very simple though. Okay, so it may look like this. Here's one with 7 inputs, and with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hidden layer neurons, and 3 outputs. And again, maybe this is risk, high, medium, and low. In fact, the SARMA example has a 3 output example in it, in the SARMA book. So again, you would have to design this based on your problem. What do you need for outputs? Okay, but we'll get into that. So these are the hidden neurons. And what do I mean by hidden? Well, middle layer or hidden will be explained shortly. Okay, so let's look at these layers one at a time. First, there are the inputs. Again, very obvious. These are the same as the predictor variables you've used before. Okay, you choose them based on having an expected causative connection to the outputs that you don't know for sure. You would like them to be relatively few in number. Again, parsimonious. Same as before, input parsimony is key. You have degrees of freedom problems. You have fewer. Yeah, this is an interesting one. Actually, it turns out fewer works better than more for most neural networks. When I got my neural networks training, we were told that majority of the time, 7 or fewer inputs would be ideal. Now, that was back in the day when we were training these things with very slow software, so there's no reason not to try more. But, you know, fewer is usually better than more. More means, of course, a data collection problem. We've talked about this. More inputs means more cases are needed also to represent the values. The first neural network I built was a neural network for a class where all I collected was their height and their waist. And I was trying to predict their weight, W-I-G-H-T. Height and waist were the inputs, and the output was their weight. And that neural network trained for several days for a small class of about 50 people and converged reasonably well, but not as good as I wanted. In other words, the answers weren't as accurate as I wanted. And that's when I realized that, gee, there's a big sort of a gender difference in body structure and style. Well, that means I had to go back and add an input, didn't I? Gender. Well, a couple things happen when you add an input called gender. First of all, it needs to have a dummy variable so that both genders are represented evenly, and I'll talk about that in a second. But then you have to have tall, thin males, short, heavy males, medium-sized males, tall, thin females, short, heavy females, medium-sized females. You have to have more variety of input cases to cover the waterfront so the neural network can learn well. As with any predictive modeling technique, more cases where more values for the variables are included in a variety of combinations allows the machine learning to do better. So the same thing we've talked about in other modeling techniques holds here. Now, let's move to the middle layer called the hidden layer. This is the mysterious part of what's going on, and the function is not easily explainable, but I'll illustrate in a minute. There's no magic as to how many you put in that middle layer. We used to have some crude formulas that we tried, you know, the number of inputs divided by 2 or squared or something like that. We had all kinds of fun. There were people trying over and over again. Back in the day, again, when the neural network training was expensive, cumbersome, and took a long time. Now, again, with the power we have, you're better off just to try. Try 3, try 4, try 5. The default for SAS Enterprise Miner seems to be 3 neurons in the middle layer. I've always thought that wasn't quite enough, but we'll see. You can vary the number to get better results. Most software does this automatically, and I think SAS has some settings where it will vary the number of neurons in the hidden layer and see if it can do better. If you have more in the middle layer, you have a better ability to learn nonlinear relationships. But fewer, you have less chance of overfitting. You can have overfitting in a neural network, and it will be evidenced the same way as it is in other models, i.e. fits great on the training data, not so much on the test or validation data. Now, I'll come back to that in a minute. I'm going to walk you through a little brief example. So output neurons. This is the answer. And there's two things neural networks are good at: predicting and classifying. Predicting and classifying. Well, those are two biggies when it comes to the world of predictive analytics. The output can be continuous, meaning interval, or categorical. It can be binary or more values. You can have the probability of customer defect. You can know whether a student will succeed or not. That would be binary. Machine breakdown likelihood, probably continuous. Is this fraudulent transaction? Yes or no? What will the customer purchase next? Lots of things. So both kinds. So they're very flexible neural networks. Well, let's take a look at one. Now, again, I've just designed a notional one. And so don't think that they all have to have 4 inputs and 5 in the middle and 1 on the output. No. It would have 1 over here if the answer is continuous, of course, because you're just going to get a number. So here are the inputs. Here are the middle layers, the hidden layer. And here's the answer. And these are the bias. The bias can be thought of sort of like the intercept or regression equation. There's a bias attached to each of the neurons in the middle and output layer. Okay? Now, what do we do with this thing? Okay. Oh, here are some of the other models. Some have, multiple outputs. That's certainly doable. Some have direct connections where some of the inputs skip directly to the output. Some have multiple middle layers. Okay. But basically, most of them are going to look like the one I showed you. Inputs, hidden, outputs. Okay, now I've changed a little bit. I've said this is going to be a binary output, either a yes, no. They graduate or didn't graduate in the master's program at UMUC. Well, we'll say somewhere else. And let's say we decided these were the key inputs: the GMAT score, Graduate Management Aptitude Test, the GPA in their undergraduate, the quality of the school they went to for their undergraduate, and a grade on a written example they submitted. Okay, so we only have 4 inputs. And we're going to try to predict whether the student will or won't graduate. Now, again, we're using past data, so we know the answer to this, just like we do with all predictive models. We know the answer. We're trying to get a model that will allow us, when a student walks into the office who we don't have an answer on, we can advise that student whether or not we think they'll make it. Okay? So what do? All right, step 1. We have to have the past data set, and we have to separate it into training and testing, just like we do for every predictive model. The neural network model will learn from the training how to relate the inputs to the outputs. The training examples must be representative and proportional for the learning to be effective. In other words, you don't want the 99-1 case, but again, with SAS, remember that's solved by basically putting in those prior probabilities when you do the metadata. And the neural network will use the test example to see how well it does. Okay. So, step 2. We're going to take the past data cases and we're going to feed them in one at a time to the neural network, along with the answer. However, there's something we usually do that almost always is required, and that is the inputs, those predictor variables. Remember, there were 4 things. Have to be normalized, okay? Normalized into numerical values between 0 and 1. So how do we do that? Well, think about the GMAT. I don't know what the range is on that. Let's say it's 400 to 800. We could say 400 is a 0 and 800 is a 1. And then, so everybody who comes in with a score between 400 and 800 is going to get a number between 0 and 1. GPA, again, an A is a 1 and a C or a B is a 0. So you come in with a 3.2, you get a number between 0 and 1. School quality would be a little tougher. The exercise would be a little tougher, but we could do it. We have to find a way to do that. But let me give you a sort of a thing that makes it a little more sophisticated. Let's say the GMAT does range from 400 to 800, and you decide, gee, I'm going to give a 400 a 0 and an 800 a 1. Makes sense, logical. That's the range, isn't it? However, everybody who applies to your school has GMAT scores between 525 and 700. Well, if you use the 0 for 400 and the 1 for 800, then basically you're squeezing all those people together more closely than you need to and not giving the neural network enough separation in terms of difference. you would be better off to say, I'm going to give the 525 a 0 and the 700, if I said that was the highest score you got, a 1. Then occasionally when somebody came in below a 525, they'd still get a 0. If somebody came in above 700, they'd still get a 1. And so you're penalizing or rewarding the outliers a little bit, but it would spread the ones you get often, the cases you have, a little bit more distant from each other over the range you want. So again, that's something to think about. If you were using gender as an input, you would have to create dummy variables for that, for categories. Why is that? You say, well, if I have gender, can I use a 0 for a female, a 1 for a male, or a 1 for a female and a 0 for a male? No, because the neural network needs to have values, and it needs to know, it assumes that a higher value is worth more. So basically, you would take gender and turn it into two variables. One would be a female variable, one would be a male variable. The female variable would get a 1, and the male a 0 if it's female. It would be a 0 for the female and a 1 for the male variable if it's a male. So we've done what? Well, we've taken just like you do with all dummy variables, we've taken one variable and turned it into 2. What if it's days of the week? Well, then we turn it into 7, and so forth. So you have to be a little careful, again, if you're trying to keep your variables limited, but that's what you have to do. You can log, transform, and probably should positively skewed variables, just like you do for neural nets. Just like you do for regression. You don't have to try it without it. And again, you normalize interval variables, as I said. If you don't normalize them, then again, the large values dominate. So everything has to be a number between 0 and 1. And again, as I said, consider an appropriate range for that. So let's say we brought case 1 in, first person from our past data set, and we've normalized his or her inputs. And here they are. What happens next? Well, these, of course, are numbers between 0 and 1. They will get pushed up. Go back. They will get pushed up to the hidden layer. But something will happen along the lines with it. The normalized inputs multiplied by random weights are pushed to the hidden layer. And remember, each input layer is fully connected to the next layer. So each one of these, we'll go back again, each one of these is going to send a number to all 5 of these middle layers. So look at this. It's going to send a number here, 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 it's going to send a number here. It won't be the same number because on each of these branches, in addition to this 0.56, it will be multiplied by a random weight. Random weights. Weights are initially random. They're usually very small, somewhere between 0.0 plus or minus 0.05. Okay, that's one popular method. Small weights. These are going to get adjusted later on. And of course, they'd be different for every connection. Okay, so for example, this 0.56 is going to have 1, 2, 3, 4, 5 weights. Each of those will be multiplied by 0.56, and that number will go here. But these weights will all be different. Every one of these green weights will be different. And of course, the other neurons will do similar things. So we're going to have 4 inputs, in this case, going to 5 neurons in the middle layer, but each of those is going to have a weight, very small weight attached to it, and it gets multiplied. 0.56 times this weight goes here. 0.56 times a different weight goes here. 0.56 times another different weight goes here, and so forth. So we have 20 weights, don't we? Or 16 weights. No, 20. 5, 10, 15, 25. 20 weights, like I said. Okay? So, now what happens? All right, so some numbers are going to show up here. In fact, this neuron's going to see a number coming from here, a number coming from here, a number coming from here, and a number coming from here. It's going to end up with 4 numbers in here. 5, 6 times a weight, 4, 3 times a different weight, 7, 0 times a different weight, 9, 1 times a different weight. It's going to do what with them? Well, we'll see. It is going to do 2 things. First of all, it's going to sum them up. Add them up. You can do other things, but summing is the norm. And then it's going to run them through what we call a transfer function. an activation function sometimes called, but a transfer function. Okay, now why do we do that? Well, the transfer function will renormalize or squash, we call it squashing the numbers back down to something between -1 and +1. Let's see how that works in a second. And then they're going to do what? They're going to send it up to the next layer. So the magic occurs here, if you want to call it magic. And here's what goes on inside each of these hidden layer neurons. Remember, it's got stuff coming in. Should have 5 here, not 3. It's got 5 coming in, adds them up, and then puts them into this function, this summation and this is summation, and this is a transfer function. And the transfer function, so the summation adds up these inputs, and the transfer function gives a new output to send to the next layer. Now, the transfer function can be one of several, okay? The one that is most popular is the hyperbolic tangent. Here it is. Hyperbolic tangent. Now, what does the hyperbolic tangent do? Well, no matter what your sum is, I don't care if your sum is 50. Let's say that when you summed it up, right here, it added up to 40. I can't add that high, but let's say it did. Doesn't matter, because look, what comes out of the hyperbolic function for an output is a number between -1 and +1. Now, if you write around 0, it varies pretty quickly, doesn't it? Just like it did for logistic regression. But if you're down here, you know, once you get -2.5 on down to -infinity, you're going to send out a -1. Once you get up here to about +3 on up to infinity, you're going to send out what? A +1. So that's why we call it a squashing function. No matter what the sum was for this neuron, it gets squashed down into a new number between -1 and +1. There it is, -1 and +1. So no matter what number you put in, the answer coming out is going to be some number between -1 and +1. Okay, so this is the input coming in here, and this is what the hidden layer neuron sends out. So what does hidden layer do with that new number, which is between -1 and +1? Sends it to the next layer, which in most cases would be the output layer. And by the way, it has another weight on it, another randomized weight. At the output again, what does that have? What happens at the output? It sums it up, and then it transfers it again. Okay? So we send all these weights up. Magic happens here. Send it up here. More weights. Let's say this squashes it down to a 0.8. It sends it up with a weight, a different weight, a weight, a different. But this is 0, the weight, and a different weight, and so forth. And then we end up at the output layer, where we have to combine the inputs and then use an appropriate transfer function to get the final result. If it's a continuous target, the answer is directly available. It's just a linear combination. If it's a binary target, we have to use, again, one of these logistic functions to convert it to a probability between 0 and 1. And then we get a number. So here it is. We come out with 2 numbers. And of course, they don't have to add to 1. Let's say this came out. This was our first case. And there was past data. So we know the answer. We know whether the person graduated or not. Let's say we run it through with the randomized weights. And it comes out this way: 0.75 probability they graduated and 0.39 probability they didn't graduate. And again, you can set it up so that these do add to 1. We would say, oh, that person graduated because this number is higher than that number. So they graduated. You know, again, you can have a cutoff that it has to be above a certain level before you'll declare them a graduate, just like you can have when you do the ROC curve, you can have a cutoff. A threshold cutoff. We can talk about that next week when we get into SAS. But right now, let's just assume we run it through a logistic thing and we come out with raw numbers and we say higher number wins. Okay? The next question has to be asked is this the correct answer? Remember, this is past data, so we know whether they graduated or not. What do? If the result is correct, we try case number 2. Remember, we got lots of cases. We're running cases through one at a time. So case number 1 went through, and they said, yeah, they graduated. If that's the correct answer, we go to case number 2, keeping the weights on all the connections that we used for case number 1. If the result is wrong, we change the weights and try again. Okay? Now, some neural networks change the weights at the end of an epoch, which is one pass through all of the cases. Other neural networks change the weights gradually each pass through a case if they get it wrong. Some recycle back and run the same case over and over again until they get it right. There's a lot of things you can do. You can tweak the weights. You can add a little momentum, which means once the weights start getting bigger and bigger, keep them getting bigger. You can do a learning rate, which says adjust the weights more and give it a little kick. So what will happen over time is the error of the whole set of cases will continue to come down for the training set. Somewhere in here, it will start turning back up for the test set. And of course, that's where you want to stop so you don't have overtraining. So it's a continuous process, feeding back. And the only thing that's changing, remember, you can't change the inputs. Those are facts. What you change are the weights. Change the weights here and change the weights there. And there are various ways to do that. Very slight changes. And you keep doing that over and over and over and over and over until you find one set of weights that gets all the cases correct, which is never going to happen for a complex problem. Or until you say, well, I'm getting 90% of the cases correct, or I'm getting no more, or I want the smallest average error for the entire set. Okay? You have to have some stopping criterion because the neural network will just continue doing this cycling until well, as long as you have electricity, until it don't stop, I guess. Now again, in SAS, you can tell it the number of trips to make through the data set, or you can tell it how long to train, hours and hours, or days and days, and so forth. But it will keep doing these weight adjustments because remember, once in a while, if it does enough weight adjustments, this number, suppose this was wrong, the person didn't graduate, you keep changing those weights, eventually this number is going to come out to be less than this number, and we'll say we got that case right. And we keep those weights and try to get the next case right. We keep those, as long as we get the cases right, we keep the weights the same. And then we get the cases wrong, we change the weights and start over. It's a very iterative process, very iterative, which is why when we didn't have a lot of horsepower and a lot of capability in computers, this was a giant problem, okay? You just couldn't build neural networks, even though the theory looked very promising. As I said, a $20,000 board was in our little PC there at the National Defense University, and even then we could only train small neural networks. We saw the potential. Now, of course, again, with the software that's out there now, you can train very large-scale neural networks. And by the way, we'll come back and revisit the latest thing in neural networks called deep learning when we get to week 12. Okay? So we continue with the training set until we meet some criteria that the user can designate. Stop if the answers for the training set are acceptable. They're all within a certain tolerance. I'm getting them all right within 10%. Or stop if the neural network's not learning anymore. In other words, it's flattened out. Stop after a certain amount of time. Or, of course, stop when the optimal set of weights works on the test set. So then you freeze the weights. And this is where you try it against the test set. Now, the way SAS works is every time it tweaks the weights, it tries it against the test set. So every time it tweaks the weights, it's in essence a new model. Think about that. Every time it tweaks the weights, in essence, we create a new model because it tries it against the test set. That can be a lot of computations. A lot of computations. Usually, of course, as with all predictive models, the neural network will not work as well on the test set as it does in the training set. The error will be a little higher. If the performance is acceptable, then you freeze the weights and say, I've got a neural network now that's ready to go. When a new person walks into the room and says, here's my GMAT, my GPA, here's where I went to school, here's my written example test grade. You think I'll make it through the grad program? We can say with some probability, yes or no. So once the network is evolved or converged as well as it's going to, we freeze the weights. They don't change anymore, and now we have an operational model once it performs well against the test set. Now, what if we keep doing this and we still can't get a real good neural network? Well, just like with any model, maybe you have a bad set of inputs. In other words, you can't predict the price of the stock market based on the price of grapefruits and the size of your shoes and whether it rained yesterday. Okay, some people think you can, but you can't. So it might be you better get a different set of inputs. It might be that you don't have enough data properly formatted and properly representing the solution space in terms of the variety of values for each variable in a variety of combinations. It might be that you need to train the network longer. Why did you stop it after 20 minutes? Why did you let it train for 2 days? It might be that the number of hidden neurons needs to be more. It might be that you need a different transfer function. As I said, the hyperbolic tangent is a common one, but you don't have to. SAS has several built in. It might be that you want to try, this would be my last choice, would be to try a different architecture. In other words, try one of those fancier, more exotic architectures. Okay. Most software performs many of the adjustments automatically. You'll see you can set that up in SAS Enterprise Minor to do so. Now, when you get the answer, as always, and this is sort of general advice that I've preached before, you can't say, oh, it got some wrong, or it didn't do as well as I'd hoped. No, no, no. The only thing that matters is, does it do better than the alternative way you have of making this work? For example, I mentioned that virtually all credit card issuers use the Hick-Nielsen neural network to determine whether a transaction is fraudulent. It will detect between 40 and 50% of fraud. Doesn't sound very good, except the best statistical models they used before that could only detect 20 to 25% of fraud. So we're talking about twice as good. Okay, now you'd like to have it detect 100% of fraud and no false positives, right? No false negatives, no false positives. That ain't going to happen. So as always, you have to compare what came out of your model with the best alternative you have. Now, a second problem. Can you explain the answer? Look how much difficult it was to grasp sort of what's going on in that hidden layer. How'd you like to explain that to your boss? It also means certain things are probably off the board. For example, you can use a neural network to determine whether someone will pay back a loan. You got a lot of past data. Let's say you're a loan officer. You just came into the business and you say, gee, I'm going to build a neural network based on all this past data. And now when somebody comes in, I'll run the neural network and I'll tell them whether they can have the loan or not. So I come in, I want a loan, and the neural network says no. And I say, why? And they say, I don't know, but the neural network says you can't have the loan. Well, I might start saying, maybe you just don't like guys whose last name starts with a K, a silent K. Maybe you'd like my K to be silent instead of Canode, just be Node. Maybe that's why you didn't give me the loan. And they'll say, no, 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 no. Why didn't I get the loan? Well, the neural network says you can't have it. Well, if you go to court and all, that could be a problem. So even though there's some good applications for neural networks, some of them aren't used. There's 2 or 3 great websites you can go to see some neural network applications. One of them was predicting which police on the Chicago police force were likely to become corrupt. You can imagine the firestorm that created, because in essence, that is profiling, isn't it? It's saying, based on your characteristics, we think you have a high likelihood of becoming corrupt. And so we're going to give you some counseling in advance. So that's not going to work. On the other hand, if you can build a neural network that predicts when a piece of equipment is going to break, that's great. No one's going to quibble with that. That's exactly what's being done. There are neural networks being used to predict equipment breakdowns. I've often told the little story of the commercial where the doorbell rings, lady opens it, and the repairman dressed in white says, I'm here to fix your refrigerator. And she says to her husband, who's sitting on the couch, this gentleman's here to fix our fridge. And the husband says, well, he's got the wrong house. Our refrigerator isn't broken. And so she says to the repairman, I'm sorry, you have the wrong house. Our refrigerator isn't broken. And he says, I know, but it's about to break. How in the world would you know a refrigerator was about to break? Well, think about it. When we get the Internet of Things going, where we put hundreds of billions of sensors in everything, including refrigerators, which already have some sensors, but all these sensors are sitting there collecting information, which is getting fed where? Well, to a mega sensor, which has a neural network built into it. And when that neural network runs and the probability of the machine or of the compressor locking up in 28 hours, 24 hours is high enough, the thing sends a message to headquarters to get somebody out here to clean out the whatever's causing that before it breaks down. So right now they're predicting major equipment breakdowns on oil rigs 2 weeks in advance out in the Gulf. That's pretty impressive. Are they always right? No, of course not. But are they right often enough to make it a very profitable endeavor? Yes. Because all you have to have is one of those things break down, and it's weeks where you're not pumping oil. So preventive maintenance, predicting fraud, identifying likelihood of people doing certain things, all those are doable. Many, many things. There was a package I used to use that cost $300, where one person used it in Pennsylvania to predict or forecast how many jurors they needed to call in each day. You know, jury duty is one of those crazy things where if you call in too many jurors, you got people sitting around getting paid to do nothing. If you call in too few, the courts crumble to a halt, and the judges get mad because they're doing nothing. They don't have enough jurors. So you'd like to have about the right number. So this person built a neural network that saved one of the cities in Pennsylvania, I think $25 million a year with a $300 software package. Pretty impressive, because you could use it to forecast how many jurors that were going to be needed much more accurately than any other algorithm they had. If you have a very complex, a lot of nonlinearities relationship, I think you're going to find that the neural network will end up being the most accurate model you can build. If it's a straightforward, fairly simple kind of relationship, the decision tree might be the best. Regression often is very competitive. And so we have multiple models for multiple situations. So can you explain the answer? Can you get the necessary inputs in a timely manner? It doesn't do any good to say I can predict the stock market close if you give me all the inputs 1 second before it closes. Well, it used to be you couldn't make any money on that. Now with nanosecond trading, maybe you can. But, you know, we need the inputs in advance, early enough in advance where we can take action. And can you operationalize the answer? How do I take this complex neural network function, because it's not something you can write out like a linear regression function or even a logistic regression function. It is a complex set of inputs getting smushed into these middle layers and outputs. In fact, you can get a patent on the final weights. You can put a patent in. If you have a neural network application that works, you can patent the final weights. So it takes a lot more work to operationalize the neural network answer, turn it into something usable. Some other considerations. Do you want to do it real time or offline? Offline is obviously easier. We are moving towards needing real-time results, such as, of course, credit card transactions have to be real time. You can't say, well, I'll call you tomorrow and let you know whether you can buy that hat. Can you do something in a spreadsheet or other interface to help? And how do you interpret the results? That's problem dependent. And again, what are you comparing it to? What else is used, and how much better or worse is the neural network? Now, here's an example. And by the way, neural networks are used for appraising houses in several counties in California and elsewhere. Here's an example right out of a book that's pretty old right now, but I've used it a long time. It was pretty good. And Barry and Linhoff are really good guys about writing books. Let's say we have all these values for a house, and we're trying to predict what the house will sell for. Okay? We know what it did sell for because, again, it's past data. These are the inputs. How long ago it sold, and what year it was built, et cetera, whether it has an attached garage, living area, and square footage. So what happens, of course, is we take a look at all our data set and say, oh, here are our features, and here's their values that range. For example, number of dwelling units ranges from 1 to 3. Plumbing fixtures ranges from 5 to 17. Heating type can be A or B. Basement garage, number of cars, 0 to 2, and so forth. Then what do? Well, we have to take that range and normalize it. So if we said the lowest priced house that sold in our data set was 103, the highest price was 250, I'll call this a 1, I'll call this a 0, then this one that sold for 171 is what? 0.4626. And this 4 is 4.1739 of the way from 0 to 23. So they normalized all the inputs. Remember, they have to be normalized between 0 and 1. Look at the model. Wow. So there's all the inputs. They used everything. And there's all the weights that ended up. Okay, they only had 2 neurons in the hidden layer. Very unusual. And their answer was a continuous answer. It was what they predicted the house would sell for. Well, this house actually sold for $171,000, but they predicted $176,000. Not that far off, right? And then what they did was then look at all their predictions and put them into categories, how confident they were. A little different approach than what we're talking about. They said, if we get an output that's 0.0, we're confident that that's 100% confident that that was the right answer and so forth. This was for a different problem. All right, some applications out there in the real world. How about this one? This one predicts whether cement that's being mixed will set up properly before you put it in the ground. Think about what that would say, because the cement that comes out with a prediction that says this is not going to set right, based on all these predictors of the various things in there, you throw that away rather than stick it in the ground and have to go dig it up later. One of my favorites, PapNet. It detects cancerous cells on pap smears. A pap smear has about 300,000 cells on it. An abnormal one has around 150 or so bad ones. Not so hard to find. 97% accurate. You know how accurate humans are reading pap smears? 50% accurate. A lot of false positives, a lot of false negatives, which is why almost all human readings are done twice. That reduces the false positive, false negative rate substantially. This is one that designs printed circuit boards. Wrangler uses one to forecast production of their genes and so forth. Here's one that optimizes the use of the OR room in hospitals. Some other application areas, there are a lot of these. A lot of people try to predict stock prices. Another anecdote, when I taught the class, I used to teach a class just on neural networks about every 2 years when I was at a different university. One of the students tried to predict the stock price for a specific stock, again, based on past data, and did a very good job. His overall, he was using overall R squared, correlation, coefficient determination. He was getting very low number, and he was getting pretty high average error. But when he looked at it, he said, I guess it doesn't work. I can't use it. When he looked at it, he found that when it predicted that the price would go up substantially, it was almost always right. When it predicted the price would go down substantially the next day, it was almost always right. It was the big gray area in between where it did a terrible job. It was way off a lot. So I said, think about this. When it says this price is going to go way up, buy the day before. When it says the price is going to go way down, buy or sell short. And the other days, don't do anything. Stay out of the stock, right? And he said, it's a great idea. I had another student who was about 85% accurate in predicting horse races at a local track, and so forth. So I've had some personal examples that were successes. So, again, you can take past data and try to predict what's going to happen tomorrow, a forecasting example. What would your inputs be? Well, you have to decide. I mentioned a company called Ward Systems. Ward Systems actually has a class you can go to 3 or 4 times a year in Florida using their software where they will teach you how to predict the stock market. And I know from knowing the people at Ward Systems quite well that they're very successful with it, okay? You can make a lot of money. And again, you're not going to make 10,000%, but what if you can do 50% better than the average investor? That's quite a bit. Again, that's substantial over the long haul. So they'll help you figure out what stock market indicators, the put-call ratio, the VIX, and all like this. I mean, I've experimented with it myself. It just takes a lot of time. People always say, well, if you like neural networks so much, why don't you use them to make money? It takes a lot of work to collect all the variables and keep training the neural network, because if the pattern changes, you need to change with it, okay? Remember, it's past data, just like all predictive models. The past data has to be indicative of the future. I've had students try to train a neural network to predict the stock market and only use inputs from the years when the market went up. well, then the neural net's never going to predict it going down because it says I've never seen it. How about profiles? This is, again, the credit rating problem. I could say, here are my predictors, and A means you paid the loan back, B means you didn't, so here are my past cases, and then I put this in and train a neural network. Here's one that I've actually done in class. There are 63 little squares here, okay? And I've handed out pieces of paper and had people make A's, B's, C's, and D's. We actually went about halfway through the alphabet. And then you input this to the neural network to learn what an A looks like. So what do you put in? 0, everywhere, every cell that's empty, you put in a 0, and every cell that has anything in it, you put in a 1, and you tell it that's an A. And so it learns these various shapes of A's. Now you go and get, for your test case, you go and get different students who make A's, B's, and other letters differently, and you have them fill out the sheets, and you turn those into your test case, and you ask the neural network, what is this? Well, if it looks something remotely like an A, the neural network will probably guess A and beat it right. If it looks remotely like a B, it'll probably guess B. If someone says, no, this is how I make my A, the neural network's going to get it wrong and say, no, that's a B. See, that's how I make my A's. So, you know. Irregularity detection. Again, detecting whether a transaction is legitimate or fraudulent based on the current transaction compared to the historical profiles. Signal classification. Anything that you can put a scope on and get a signal, you can convert that to a neural network. It may not be a predictive neural network, but it can be a neural network. For example, sonar. The Navy actually uses neural networks instead of humans to read their sonar. Okay, here comes a sonar reading across the screen, and the amplitudes of this are what get fed into the neural network, and it's trying to predict whether that's a rock, a head, or a metal cylinder. Metal cylinders are bad because those are depth charges, and bombs, and stuff like that. This is also used in by anesthesiologists to adjust anesthesia. It's used to detect pulp wash in orange juice. You put a scope on the orange juice and get certain amplitudes over time, and you feed those in. It says, no, there's pulp wash in there. You're not allowed to put pulp wash in orange juice from Florida, and so forth. I mean, it just goes on and on and on. It's really interesting. New construction. Suppose you were in the construction business and you'd like to figure out whether this construction is going to be delayed or what it's going to cost and so forth. You could predict that. And some construction people are starting to use neural networks. Predicting who'll buy something or who'll contribute. Yes, again. Okay. Strengths and weaknesses. The strengths are, of course, we can handle a wide range of problems. Predicting, categorization, wide range of problems. We get very good results, usually better if the situation is very complex, nonlinear. We get better results, more accurate results than we do with regression or decision trees. The weaknesses, well, as you can see, a lot of massaging of data, a lot of capturing of data, not a very good ability to explain exactly why the inputs cause the answer. Okay. So looking ahead, what we're going to do is go through the SAS approach to neural networks. They've got 2 or 3 really good options in there. Again, as always, you should be looking for a good data set to use for a neural network. Same as always, we'd like to have a data set with a robust feature set and lots of cases. And so next week we will look at the SARMA thing. And we're back to my final slide as always. Now I will say I will post in the news section the links to a couple of more places where you can see more neural network applications. I will also mention that if you're just interested in neural networks, predictive or otherwise, there is a package that I've used in class that's relatively easy to learn called Easy, E-A-S-Y, EasyNN, one word, just EasyNN, and it's free. So you can go get that, use it for free. I think you can buy a purchase version for about $50 too, but it's pretty neat. It's got some good tutorials, walks you through it. I'll put a screenshot in because one of the things I like about it is that you can get, when you get the final answer, you can see visually. Let me bring up that screenshot. Let me I'm doing it in a second. This is it. Yeah. So this is a screenshot from a result of a neural network out of EasyNN. This was to figure out how many diggers and spades and diameters you needed, to how many kilograms of rock they were going to be able to dig out in a day. The example doesn't matter. What's interesting here, I think, is that, first of all, visually you get to see the strength of the weights. You know, the bigger the weights, the more influential that input neuron is on the answer. So you can see the number of shovels or spades they had, the diameter of the hole they're going to build had big influence on how many kilograms of dirt they're going to dig. You can also see that some of the weights are negative and some of the weights are positive, just like in a regression equation. Some of the coefficients or the fact features are negative and some are positive in terms of coefficients. You can go up here and see, if you get the full blown, you don't see it on this one, but you will basically get to see what which cases have the biggest errors. And again, you might want to go back and look at those cases and say, "Ooh, that was a weird day. We don't want to use that case," because sometimes one or two really weird cases can cause the neural network to really crunch, because you said, "I'm not stopping until I figure out." The neural network figures out how to get a good answer for those cases, which skews everything. Of course, when you're dealing with average error for the whole data set, it mocks NICs, but that's not always what you're dealing with. So anyway, I thought this was interesting. Called EasyNN. It's a pretty neat package. Okay, so we're at the end. Again, as always, you can ask questions now if there's something that's still confusing, or if you want to think about it, ask during the week. And of course, as always, personal phone call or email for any kind of personal crisis. It's pretty interesting stuff, I find. I mean, to me, it's one of the more interesting aspects. It's nice to have a whole arsenal of tools to use: decision trees, regression, neural nets. And by the way, neural nets, again, can deal with continuous or classification problems. So it's nice to have tools we can use, and then it's nice to have software like SAS-EM, where we can apply these tools pretty quickly and then put a compare node at the end, model comparison node, and compare multiple models of the same type and multiple models using different techniques, which will lead us to, after we get done with the week on neural nets next week, week 9, week 10, we'll talk about ensemble models. Some of you already did one ensemble model with the decision trees, but we'll talk in more depth about ensemble models. Okay, well, what I'm going to do is my usual thing. I'm going to stop sharing. And back to the main screen. And then I'm going to go and stop the recording.